All right, so I'm going to make the problem 387 in the doing FEA. All right, and so okay. Starting it out at the wall right here, and we find out that's 1.5 is the diameter, and it's going to be extruded by I should have this out. They said 2 inches. Boom, 2 inches, and then building off from here. Sketch onto here, and now this is going to be 1 inch. Alright, and this is going to be extruded out 9 inches. So 9 inches. And then did they tell us this diameter of this? Yeah, they do. Okay. So right onto the end of this. Yeah. Okay. It's gonna be fine. I think I could do this. Yeah. So I have to do like just a little trick onto the thing. I think. Nah, I should be fine. So this one they also say is 1.25. So no, 1.5. And they say it goes out 2 inches, but I'm going to make it go out 4 inches because you can just tell by the picture that it has to go out 4 inches. So 4 inches, boom, right here. But now we want to see this thing from the side, and I want to draw on this front plane, sketch on here, and I will sketch. But I want this thing, it needs to come out. I'm going to use the center line from the origin and make the thing come this far. And this distance is 2 plus 9 plus 2. Right, so is that 13 inches? I think it is 13 inches. And I'm going to draw a circle here. And this thing is 3/4 of an inch in diameter. So 0.75, smaller. And I think I got it. Okay. And select C, and we're going to extrude that guy. And that's going to extrude 12 inches. Whoop, it did not work. 12 inches, boom. Right. Now, just to make this interesting, I'm going to actually model the wall. And not much of the wall, but just some of it. And I don't know, I was thinking about making it, it doesn't need to be much. I'll go 2 inches. Now, I guess I'll make it bigger than that. I'll make it 4 inches. There you go. And make it 4 by 4. Just see what happens, right? And I'm going to extrude that by just like, let's just make it an inch, right? Sure. So it's just so that it doesn't matter. It's just something to grab a hold of, for the FEA. So I'm going to add simulation onto this. Little simulation, create a study, static. The part, they said it was cast iron. Let's make it cast iron. Why not? It doesn't matter. But they have iron. What did I say? It was gray iron, right? Gray cast iron. Boom. And what are the strengths of this? Right? Is this in PSI, right? English, yeah. So you see that it has compressive of 82 and a tensile of 21, right? So that's not the same. That's not the ASTM 60. What about this guy? Yeah, it's still got there. But anyway, you could see that they have a difference in compressive in there. But we'll find. We applied that, and they even changed the color for us. Wasn't that nice? We skip connections. Go right click and go to fixtures. Just grab a hold of that. It doesn't matter. Right there. All right. We're using that as a piece so that we don't get influence. Oh, I forgot to do something. Sorry. It's okay. It's not going to hurt anything. I forgot to put the fillets in there. So the fillet is 1/8 of an inch. So I think we'll be able to fit that in there. We have to be careful. So the fillet is right here. And we're going to go right to there. So 0.125. Boom. Yeah, it fits in there. Right. We could have even gone up larger. But now the fillet is in there. And that's awesome. We might, something I've done in previous ones that you might notice that I do is I insert curves and split lines. And I'm in the intersection here. And for the intersection, I'm going to use the front plane and the right plane. And I'm just going to intersect that right there. Whoa, it didn't do that. So it didn't like that top plane. There you go. There you go. See? Now you can see that they do interface of this. Front plane, top plane. Okay. That just added lines in there. It's just going to force it so now there's going to be definitely a node that's going to be at one of those points. And I might actually even change the split line. It doesn't hurt anything to put it on this face and put it on that face. And to put it on all these things, right? It helps often to be able to have nodes right where I want them. It just works out well. So going back to the static right there, we could end that afterwards, by the way. And the load is just going to be upwards, right? So we need to select direction, pick on that face. We're going to go in English units, and that's the right direction, okay? And what did we put onto there? 250 pounds. Kaboom. And now we can, let's just accept the regular mesh before anything's said and done. So you can, this being that cast iron is very dark onto the thing, but you could see the mesh is rough right here. And we will we'll run. Okay, so this happens quite often. When you put a large load on something thin, it could deform too much, and what you have to do is run a non-linear thing with excessive displacement. So it's running a different solver right now, which ends up having to do an iterative process. So you might see this convergence plot as the thing does iteration after iteration as it's trying to reduce the error onto the thing. So it was able to do it, but it definitely complicated the solution. And it's showing us von Mises stress, which is not quite what we haven't covered it yet. We do want to turn this into, we can't turn this into KSI. That's kind of nice. So we'll turn it into KSI. Let's take a look at the stresses, normal stresses in the X direction. We do have the first principle stresses, so we could do that. That's the thing we were looking for. So let's make sure that's what we end up with, those first principle stresses. So that's the way we could compare the thing to. And we can show we can have max annotation, but that actually happens like over here, so that doesn't help us any. And let's come up to here and go to 0. And for our maximum, let's take a look. What are we predicting? I can't remember. We're predicting that we're going to have a principal stress of 52. 52. So let's go to 50. That's nice. And let's make it floating and get us 1 decimal place is good enough. And the color options, 10 is good. Let's make our discrete. Interesting, right? Take a look right there. That's where we're finding this principal stress is largest. Let's go to list selected. And what we find there is we have a maximum of 49 and an average of 31. We could even plot what that looks like along the lines, right, as we seem to come through here. While we're doing this, like a little analysis here, as we're trying to do some investigation, let's actually put that mesh on top. Superimpose it on there so that it gives us a better idea. And you can see that's really happening at one node. So in order to really assess this, we want to increase the number of nodes right here. And if you saw the other video for this, you'll know that we do apply a mesh control. And I'm going to put it around these locations right here all the way along. I'm going to do it all the way around. I don't actually have to do it all the way along. In fact, maybe I could save some time because I do have a nonlinear thing going on. That's mostly probably because of the amount of displacement on this thin little woofy part right here. But let me ramp up what the fine is on here, and let's just see what happens. Alright, so I'm going to create a mesh. By the way, I don't like to see the mesh controls, so I'm going to hide them. Create a mesh, and they tell us that's going to destroy everything. So I don't care. I'm telling you to do it anyway. And you can see that the mesh is improved. Let's do that thing again. Are they good? I think they already accepted the fact that we have to run a nonlinear thing. It's because the nonlinear thing comes from that the geometry changes because you think about the position of the force with respect to the force thinks is going straight up and down, but if you have enough of a deflection, the direction of the force starts to have an angle to it. That's the nonlinear part of it. So you have to do an iterative solver. But now we take a look and we could see this is the location or thereabouts where we think we're going to have the most. Let's go and list the selected here. I guess we have to choose that edge afterwards. And we can see we have a 52.7. What were we predicting? We were predicting a 52.49. That's an interesting thing, and let's see what that looks like. Yeah, like right in there. So it's getting just before it gets in. Can we get any better than that? That's the question. Or will it change? How sensitive is it to this mesh control? So I'm going to edit this definition, and I think I'm going to go downwards in here, and I'm going to go downwards. And by the way, it has a limit to how far it'll let you go. It'll get angry and it won't mesh. It can get very frustrating when it won't mesh. But there is a limit to it, just to make sure you know. Yep, there you go. See? Does it all the damn time. So I had to go backwards and just had to monkey with these things. And like I tried for too much at once. That's it happens all the time. Trust me. It can be frustrating. Yeah. And then once it seems to me that once it doesn't work, it really doesn't work. Sometimes I think that might help. Yeah. Yeah, see how close now, look, see how tight these are? Yeah, that's pretty good. That's pretty good. And let's run it. Once again, I get bored waiting for the thing, so I turn that convergence plot thingy on just to see if it's doing anything. Because sometimes it just kind of like sits there and spins, and it's boring. I'm gonna get a guitar and start playing soon. Boring. You're boring me. Don't bore me. Don't bore me. Hurry up and solve. By the way, this used to be all the time. I used to wait forever for any kind of small job would take, it could take a half hour for a model to solve. And it could just be a small model like this right here. In fact, this one could actually take multiple hours because I've gone crazy with the mesh onto the thing. It's something that you kind of had to be disciplined not to do back when it took a really long time to mesh things. And mesh and solve things. The meshing can take a really long time too. So let's see, what's the results? All right, it looks like you're done. Nope. Equilibrium iterations. You can see that we have 300,000 degrees of freedom. That's a pretty big model, based on the old standards. But it's the nonlinear aspect of this thing that's really messing stuff up for the large displacements. Yeah. Okay, so it decided to solve. It's looking, that looks pretty good. You see the number of, the stress contours that I decided. By the way, check out that stress contour. That's nice, right? That's a nice distribution. I like the way that looks. Okay. List selected. And 54.5. And we got, look at that. A distribution right there. We had 52.5. It's close. I have a pretty good feeling about this, the answers to this thing. But you can also see that, in the big picture, it's probably going to fail right here before it fails like right there. That's something that we need to start thinking about. Like where's the worst spot on here? So let's see, one last thing that I want to point out is I'm going to turn off these mesh controls, or actually I'm going to edit them, and I'm going to get rid of them off of this face. What would happen if we were to place them onto here instead? As I'm concerned about this is actually a sharp corner right here. So let me dumb these down a little bit. Let me hit reset. And let's mesh. All right. I didn't actually do anything. Okay. I might end this video. It's already gone long enough. Let's see, how long is it? No, 18 minutes. That's enough long. That's a long enough video. We don't want to go too much longer than that. I'm going to end it because I'm tired of waiting for these convergence plots. Long convergence plot. I'm going to make some coffee. K-Cup to the rescue. So you get a question. It says homework didn't get turned in. Turns out 11 was not submitted for some reason. I just submitted it on Whiteboard. I think there might have been a Wi-Fi issue at the time, hence why it didn't go through. Great, so I get to great to do this. Good news for me, yay! Just joking. I'm just joking around. I don't care. Let's see. I'm tired of your convergences. You're boring me. Don't bore me. Yeah, we used to have computer programs that would have little messages that say, go get a cup of coffee, because it was going to take a while. There you go. Anyway, I was going to start to point out how the stresses could just get larger and larger at that spot, but it's not worth it. So that's the end of this video, and I hope it was useful to someone.